there. This is Dr. Pratima, Faculty in Physics, Institute of Aeronautical Engineering, Hyderabad. I'm here with you with the topic Compton Effect, which is one of the topics of your first module of the subject Waves and Optics. I hope you have followed my previous video lectures, which has the introduction of the quantum mechanics, the blackbody radiation, photoelectric effect. If you want to follow those videos, the links are provided in the description given below. You can look into the videos so that you can get a continuation of the subject. Now let us look into what is Compton effect. Compton effect was first observed by Arthur Halley Compton in 1923, for which he was awarded the Nobel Prize in Physics in 1927. This discovery was of immense importance because he could explain that light cannot be seen purely as a wave phenomenon. And he was able to convince the scientific community that light can behave as a stream of particles named as photons, whose energy is proportional to the frequency. That is, the energy, he was able to give the relationship between energy and frequency. So, what exactly is the Compton effect? He was able to take a monochromatic radiation. Monochromatic radiation means what? Any radiation which is having single wavelength. Then you call it as a monochromatic radiation. Take a beam of the monochromatic radiation. It may be either X-rays or gamma rays, and take it of high frequency and allow it to fall on a substance of low atomic number like carbon or graphite. Then the beam is scattered into two components. What are the two components? One which is having the same frequency or wavelength as the incident one, and the another one is a change in the frequency which is lowered and a wavelength which is enhanced. So you are saying that there is a change in the frequency, hence the radiation which you are incidenting is modified. Modified means a change. So the change in the wavelength here from the incident wavelength is called as a shift of the wavelength, and it is named after this scientist who have studied it as Compton shift, and the whole effect is known as Compton effect, and this scattering phenomenon is known as Compton scattering. Looking into the insight of what exactly is happening, if you take an electron, predicting it as if like you are studying the properties of the material which is consisting this electron and allowing a photon to incident onto it. So this is the photon. Okay, so this is impinged onto this particular electron. So this is an incident photon of what? Of the monochromatic radiation. So monochromatic radiation, in the sense it has lambda, right? One lambda, one wavelength. So, and obviously this has E is equal to h nu, already we know about it. And now what will happen to this particular electron and what will happen to this photon? So this photon has an initial energy E is equal to h nu. E is equal to h nu. So what will happen now to this particular energy of photon? Once this hits this electron, what will happen is this photon's energy is given to or imparted to this particular electron, and this electron travels with some velocity v. It gains the energy of the photon, of this photon, and takes another path which is called as a recoiled path, hence you call it as a recoil electron. It's just like how you trigger the gun when the bullet is ejected out. Okay, you might have learned this in your previous standards. So what will happen now? The electron is moving with some velocity p. As this electron has absorbed the energy of the incident photon, now what will happen to this photon with which its energy is lowered? So its energy being lowered, this photon travels an altered path. An altered path means this is the initial path, and it travels an altered path, making an angle theta with the initial path. Initial path in the sense incident way, incident direction. This is the incident direction. And let us take phi as the angle which the recoiled electron makes with this particular incident direction of the monochromatic radiation, that is the photon. So what exactly is happening here? When E is equal to h nu, and E is equal to h nu here also, but what is happening here? There is a change here. What is the change? The energy is lowered. So the lower energy, let me take it as E nu. So E nu is equal to E dash, E dash. E dash is equal to h nu. Let me take nu as c by lambda. You know it very well. So now, what is happening to the new energy, which is E dash? It has lowered. So once the energy is lowered, seeing the inverse proportional relationship, what will happen to the wavelength? The wavelength is increased. That is, the wavelength of the incident photon, after it is undergoing scattering, is moving ahead with a larger wavelength. Larger the wavelength, lower the energy, it means lower the penetration power. Lower penetrating. I will use this property towards the application of this particular effect later in my last slide, so please remember this. So now, what do you understand this? This is an inelastic scattering, right? This is the best example for inelastic scattering. And this change in energy is not consistent. It's not orderly, it's not consistent all throughout, this change in energy. Hence, you also call it as incoherent. You can describe it as incoherent scattering. So this is all what is happening in the Compton scattering. And this description I have given for you in this slide. You can read those and you can take a note of it. Try to understand each and everything, don't by heart. Okay, let's move ahead. What really did Compton do to explain this in a mathematical way? He has already the Einstein mass energy relation, E is equal to mc square, right? You know it very well. M is the mass of the particle, C is the velocity of the light, and E is the energy possessed by the particle. And we know the very well postulated and proved E is equal to h nu formulae. Okay, take these two and equate these two. Mc square is equal to h nu. And we know that, yes, let's take it as it is. M is equal to h nu by c square. What is the momentum? Momentum P is equal to momentum of the photon, which is being instant. P is equal to mass, effective mass. M is effective mass of the electron times the V. What is V? V is the photon's invariant velocity with effect to its frame. So what does it mean? I'll take it now as P is equal to mv. So what is m here? H nu by c square into v. Hence, since it is photon's frame invariant velocity, you can take it as c. So what will happen? This and this gets cancelled. You arrive at h nu by c. So this particular momentum he has taken, and he further moved ahead, taking the concept that though there is a decrease in the energy of the scattered photon and the electron moving in a recoiled path, gaining certain velocity, he considered that the whole momentum of the system remains conserved. So he took the principles of the conservation of momentum and the conservation of energy. So what is conservation of the momentum? What is happening first? First, the photon is coming and it's hitting one electron, right? So it has this is the electron, and this is the direction, and if you take like this, okay, then this particular photon, incident photon, undergoes an altered change of path with lowered energy, and this electron takes another recoiled path. You call it as recoiled electron, and this we have taken it as theta, and this we have taken it as phi, the angles made by the scattered photon and the recoiled electron. So the here you have to understand that the momentum as well as the energy are taken into consideration by the Compton as being possessed by both photon as well as the electron. This system has only two entities, right? One, the incident photon and the electron. So now if you take the conservation of momentum, then what should you do? You have two stages here. One is before collision and after collision, or otherwise I can call it as scattering. Okay. So before scattering, the sums of the momentum, I can write it as P in short form, momentum of the electron and the momentum of the photon. And if you consider the scattering, after scattering, the moments of the electron plus photon, momentum of the photon should be equal. This is known as conservation. You know it very well. The same with the energy. Of course, here he have taken the electron has 0 for his further considerations to get the final formula, which will arrive at the next slide. The same with the energy. What will be the sum of the energy of the incident photon and the electron which is at rest should be equal to the sum of the energy of the recoiled electron and the scattered photon. Okay, hope you have understood this. So let's move ahead. He has taken this into consideration and he has done a very big formula for you in your curriculum. You need not do all those things. Just understand what the initiation he has taken for, or what are the basic principles he has considered for his derivation. Okay, so finally he have arrived at this particular equation, which says that lambda dash minus lambda is equal to h by m naught c into 1 minus cos theta. So what is lambda dash minus lambda? Lambda dash is the wavelength of the photon which has lowered energy, that is enlarged wavelength. So lambda dash is greater. So lambda dash minus lambda. Lambda means the photon which is incidenting, having its initial wavelength. So this is a change in wavelength. You call it as change in wavelength, or otherwise a shift in the wavelength. When you take the difference, you call it as a shift in the wavelength. So is equal to h by m naught c into 1 minus cos theta. Okay, of course, this has a very good significance named after Compton, and in further explanations, which is not needed for you. So this change in the wavelength, you can also name it as d lambda. What do you observe here? It's not dependent on the wavelength of the incident photon either, and it is not dependent on the nature of the scattering material. It's just dependent on theta alone. That is, it is only dependent on the scattering angle. So moving ahead, what exactly is the experimental setup? Compton have taken a monochromatic beam of X-rays. This is the X-rays coming from a source, and he has used all the rays to be filtered into a fine beam. So for that he has used collimating slits. So from this collimating slits you will get fine beam of X-rays here. Okay, fine beam of X-rays of one wavelength lambda, because they are monochromatic, and he allowed them to fall on a graphite target. And now once these photons of X-rays fall onto this particular graphite target, they are scattered at different angles, right? At different angles like this. So the theta varies. Theta varies from lower to higher values. And he has collected for every theta all the intensities using an X-ray spectrometer which has a detector. So this detector collects all the intensities for different values of the scattering, that is as different scattering angles you call it. So now what will happen further? He has taken, so now for every value of the scattered angle, he has plotted graphs taking the intensity and the wavelengths, that is intensity along the y-axis and the wavelengths along the x-axis. And for theta is equal to, he has taken for 0 and he has increased for an increased scattering angles of 45, 90 and 135. For 0, it is the initial beam which goes straight, right? So it is just the incident beam, which you call it as the primary beam. Okay, the primary beam. So because now we are getting a new part being evolved out. Let's see. So once the scattering angle has enhanced to 45 degrees, there emerged a little bump. And if you take the difference between these two intensities, that's where you get the wavelength shift. And when theta is increased to 90 degrees, the shift in the wavelength is increased. And when as the angle increases, it increases and increases more. So this is how he could take the wavelength shift. And all these values were able to match with his particular values of the experiments were able to match with his particular proposed theoretical explanation. So holding on to this, I want you to look into a paper where educational X-ray experiments were done in their lab with a portable setup. See, this is a portable setup where they have characterized cultural heritage objects towards the studies of XRF measurement, where they have taken AG anode and a scatterer, and scatterer will be the object which you want to study, right? Object which you want to study, and this is the silicon pin detector. So this I have given for you to take inspiration. Whatever you learn throughout your course of BTech, try to implement it in your lab or in your future as research. So coming to the application part, before I start the application part, I want you to recollect or recall what we have learned when seeing at what exactly is happening in the Compton scattering. What exactly happened? Recollecting it, the incident photon is hitting the electron. The electron recoils, taking the energy from the incident photon. And what will happen to this photon? It has given away its energy to the electron. It has lower energy. With its lower energy, it just takes an altered path in a different direction. Suppose if it has enough energy, it may even continue the same procedure with a few electrons. Of course, Compton has taken that he has taken only the scattered photon will be interacting with a single electron for all this particular discussion, whatever we have seen. So the point which I want to stress here is there is a decrease in the energy of the scattered photon. Decrease in the energy of the scattered photon means increase in the wavelength. Increase in the wavelength means, what does it mean? Decrease in the penetrating intensity. So when there is a decrease in the penetrating intensity, this is very safe. Towards what? Suppose if you can use this particular scattered intensity, it can even be shown in the sense illuminated onto human tissues, like into our skin, like what you see in your radiation therapy towards healing of cancer patients. So this has immense use in radiobiology because radiobiology involves interaction of the gamma rays and even high energy X-rays with atoms in living beings and is applied in radiation therapy. Not just this, you can even enhance this towards your material science applications. If you are studying any matter You can probe the wave function of the electrons in the momentum representation. And even you can study the electrical and magnetic properties of the materials using this particular concept of Compton effect. Here is the paper for you if you want to look how the electronic and magnetic properties of the materials are studied. So I want to end up this video lecture with my favorite quote of Arthur Compton, where he declares science as a language and as a powerful force which unites people globally. The benefits of science are not only material ones, the truths that science teaches are of common interest the world over. The language of science is universal and is a powerful force in bringing the peoples of the world closer together. Wishing you all the best and hope I see you in my next lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.